So welcome to lecture 8 of the Statistical Thermodynamics for Engineers. If you recall, in the last class, the last lecture, we said Nj is equal to Gj exponential alpha plus beta Ej minus plus 1. This was the most probable distribution, and this was perhaps the only distribution. But there are a few points that we mentioned over there. One was this alpha and beta. These two Lagrange multipliers were actually unknown, right? They are not known at all. So we decided that how to get around it. Okay. So the most probable distribution is incomplete. As alpha and beta are unknown. Okay. So let us now therefore do a simple thing, because we have to find this in some way. So let us seek a relation between entropy and total number of available microstates for an isolated system. Okay. So that is, let us do that between entropy and the total number of available microstates for an isolated system. Okay. Now we also know that each microstate is equally likely. A macrostate becomes most probable when it is associated with a large number of microstates. So W is basically what we call the thermodynamic probability. So this is the journey we are going to undertake, that we have to find out that alpha and beta, but at the same time we have to find out a relationship between entropy and the total number of available microstates for an isolated system. Okay, so for doing that, let us assume this kind of a configuration. Let's assume that this is a chamber that is completely isolated from surroundings. Okay, so this has got a valve. So there is a part of the chamber and there is a B. A has got a gas, B is vacuum. Okay, so this is a valve. Okay. Separating the chamber A from chamber B, which is separated by this valve. Okay, and there is a gas in chamber A. So when the valve is opened, what will happen? Gas expands into the vacuum. So the gas from here will expand and go there, right? So entropy, as we know, entropy S, okay, from your macroscopic understanding, must increase must increase as the process is irreversible. So we have suddenly opened the valve, right? It is not like a slow transition, so you can go back. So you have just opened the valve suddenly, and so the gas will expand and go from chamber A to chamber B because B is vacuum, and so the gas expands and the process is irreversible. So therefore entropy, the quantity entropy must therefore increase. So this is given, right? Now from a thermo perspective, W, or the thermodynamic probability must also increase due to process irreversibility. Correct? Process irreversibility. Okay. This is the simple reason is the final state is more probable than the initial state. Right? Initial state is that the gas remains in chamber A and it does not go to chamber B. So that has also got a probability, but obviously the final state, which is the gas fills the whole container, both A and B, is a much more probable scenario, right? So therefore, the thermodynamic probability, or W, must also increase due to this process irreversibility. That is supposed to happen. So therefore, what we can say is that entropy is definitely therefore a function of this thermodynamic probability. So if this is entropy, we don't know what function it is. It is definitely a function of this thermodynamic probability. All right. So the entropy should be a function of this thermodynamic probability, and as entropy increases, the thermodynamic probability also increases. We do not know how they are correlated with each other, but we definitely know that this should be the situation. Now, since A and B are independent, right? Independent subsystems. All right, independent subsystems. Therefore, the entropy of A and B is basically entropy of A plus entropy of B. Okay, whereas the probability of A and B, thermodynamic probability, because they are independent, must be WA into WB. Correct. Okay. So what we are stating over here, that this entropy must be related to this, but this is an additive quantity and this is a multiplicative quantity. So the only function then that can actually do that, is basically your S is given as K ln W. Okay, because logarithm is the only operator which can do that, multiplicative to additive. So SA plus SB is actually equal to K ln WA plus K ln WB. So since they are within the logarithmic sign, so you know that they can be multiplicative. Okay, so this K, the constant that sits, okay, is basically called the Boltzmann constant. Okay, so in other words, we can say that S is therefore K ln the most probable distribution, right? So K ln W, as we already got, is summation over J Nj ln Gj plus minus Nj by Nj plus minus Gj ln Gj plus minus Nj divided by Gj closing the bracket. All right, so this is how it goes. So the most for the most probable distribution, Gj plus minus Nj by Nj. This we already know, exponential alpha plus beta Ej. Let's call this 1. Okay, or in other words, we can call this Nj by Gj is equal to exponential alpha plus beta Ej minus plus 1 raised to the power of minus 1. So this is 2, relationship 2. If you multiply 1 multiplied by 2, okay, you get Gj plus minus Nj divided by Gj is equal to 1 minus plus exponential minus minus alpha minus beta Ej close bracket minus 1. So this is basically your expression 3. Okay, so now, so if we name this expression now, which we have over here as A, let's put it as A. Okay, so what we can do is that putting 1 and 3 in A, in expression A, we get the most probable distribution equal to summation j Nj alpha plus beta Ej minus plus Gj ln 1 minus plus exponential minus alpha minus beta Ej close bracket this. Okay, now since your S is equal to K ln WMP, okay, so therefore S will be equal to K summation J Nj alpha plus beta Ej minus plus. So you write it in the next line Gj ln 1 minus plus exponential minus alpha minus beta Ej. Okay, so that's what you get, and then you can simplify this a little bit further. K n plus beta E, as you can see, minus plus K Gj ln 1 minus plus exponential minus alpha minus beta Ej bracket closes. Okay, so this is what you get as an expression for entropy. Okay, but again you still retain the terms alpha and beta, as you can see. So those are not yet anchored, that what you should do about it. Okay, so in that particular case, if you recall from classical thermodynamics now, okay, what do you recall? That your okay, this you know from your classical that this is how entropy change is written, right? So it is in terms of the 3 variables: energy, volume, and number. So this is what it is. So therefore ds into dE if you keep. So this is a partial, keeping V and N constant is equal to 1 over T, which is nothing but K beta. You got the point. So if you differentiate now with respect to V and N being kept constant, okay, you will get 1 over T. So that is what is your K beta. K beta. Understood the point, right? And similarly, ds by dn, when you keep E and V constant, is equal to minus mu over T, which is equal to K alpha. Okay, so K alpha and K beta. So this gives a unique opportunity that now you know that what is the value of K is the Boltzmann constant, so alpha and beta you know. So therefore your beta is equal to 1 over kt. Alpha is equal to minus mu over kt. Okay, so you see that what we have done over here, we have taken from the macro equilibrium, or we have taken the definition of entropy, and then once you differentiate it with respect to V and N, keeping the other two constant, you get this is dt, right? Because that is what you are differentiating, and this should be your K beta, right? This should be your K beta to begin with, right? Similarly, when you actually differentiate it with respect to E and V, with respect to N, keeping E and V constant, then this becomes minus mu by T, so that becomes your K alpha then, okay? K alpha. So this gives us then the unique opportunity to find out what will be the value of beta and what will be the value of your alpha. Okay, so therefore, go to the next page. Therefore, S is written as E minus mu N by T. Now we can substitute. Okay, mu N over T minus plus K summation J Gj ln. Okay, I'm writing this ln, the bracketed terms down, minus plus exponential minus, now we have everything, J by mu by kt. Okay, close the bracket, close the second bracket, close the third bracket. So the final equilibrium particle distribution, final equilibrium particle distribution becomes Nj is equal to Gj divided by exponential Ej minus mu divided by kt minus plus 1. Okay, so in this particular case, your mu and t are from macroscopic world, through the Lagrange multipliers. Okay, so parameters like temperature are therefore statistical concepts. That can be only defined for an assembly of particles, Okay, so what we have done over here, just to have a quick recap, this becomes your final equilibrium particle distribution, depending on whether it is a boson or a fermion. And mu and t, the chemical potential and temperature, are from the macroscopic world, enters through the Lagrange multipliers. And the important concept is that parameter like temperature is basically a statistical concept that can be only defined for an assembly of particles. So this is like a new insight of what temperature is. So what temperature can be, right? Okay. So let us take an example problem so that you understand it the best. Example problem. So there is, say, a new fundamental particle called, say, boileron. Okay, so number of ways. So this is just this particle may not be there in the real life. This is just an example. Number of ways in which Nj boilerons in energy level Ej can be distributed among Gj energy states is given as, so we are giving you the distribution given as Wj is equal to 1 over Nj bar Gj minus Nj factorial square. So now the energy, what we know, the energy of an isolated system of boilerons is fixed, but total number of boilerons is not fixed. Okay, and of course your Gj is much greater than your Nj. Okay, and of course your beta is therefore 1 over kT. Okay, so the number of microstates for such boilerons, microstates per macrostate. How is it given then? It's Wb multiplicative over J, 1 over Nj factorial, Gj factorial, Gj minus Nj factorial square. Now if you take a log of Wb, you now have a summation going. J and this 2 comes out, 2 ln Gj factorial minus 2 ln Gj minus Nj factorial minus ln Nj factorial. So next what we do, we apply Stirling's approximation. So there can be numerous problems like this, obviously, where we say that ln Wb is equal to summation j to Gj ln Gj minus 2 Gj minus Nj ln Gj minus Nj minus Nj ln Nj minus Nj. So it's a very long expression, as you can see. So now what you do, you differentiate, right? You differentiate. So in the differentiation, what happens? Right. So 2 ln Gj minus Nj minus ln Nj dNj. Correct. Okay. Now there can be only one Lagrange multiplier using Lagrange multiplier. There can be only one Lagrange multiplier in this case. Okay, so that is given as d ln Wb into j 2 ln Gj minus Nj minus ln Nj minus beta Nj dNj is equal to 0. So therefore, ln Gj minus Nj square by Nj is equal to beta Nj. Since Gj is much greater than Nj, okay, so therefore Nj becomes equal to Gj square, because this is a much smaller number, and exponential minus Ej by kt. Okay? Okay. So this is a fantastic piece of thing which shows that, okay, if you have a situation where an unknown particle is given, but you know the rules, what is its energy distribution, etc., particle distribution, you can find out what will be the equilibrium particle distribution. So this is the equilibrium particle distribution. Okay, so that is what it is. So this is the equilibrium, the most probable particle distribution. Okay, so that is that. So next we will try to see that what else we can do with the Bose-Einstein and the Fermi-Dirac statistics. We've covered Bose-Einstein, covered Fermi-Dirac statistics. Now we want to know that what will be for independent isolated particles, what else can we do? For example, let's look at what we call a dilute limit approximation. So that is what we are going to cover in the next lecture. But I think you have understood now from this lecture that how to proceed to solve problems like this.